When radioactive atoms disintegrate, the changes which take place in the nuclei depend on the type of radiation emitted. We are going to look at the balanced decay equations for alpha and beta radiation. Alpha decay. When a nucleus emits an alpha particle, its atomic number will decrease by 2, i.e. a loss of 2 protons, and the mass number will decrease by 4, i.e. a loss of our 2 aforementioned protons and 2 neutrons. Here is how we show that in a balanced nuclear equation. So here you can see we have radon 222 and we have lost an alpha particle. So this is essentially a maths exercise. 222 minus 4 is 218. 86 minus 2 is 84. And then if you use atomic number 84 and look in your data book, you'll find that that is the number for polonium. So that equals X. That's the substance that you're looking for. Here is a different way these questions might be phrased for you. You might be asked to write a nuclear equation for the alpha decay of a species. Here we have the alpha decay of polonium 210. So the first thing to do is to write out the initial species that we've got, and we know that it's going to be alpha decay, so I always put an alpha particle in first, and then it's count the numbers. 210 minus 4 is 206, 84 minus 2 is 82, and again using our periodic table to find out which element has the atomic number 82, we find that it is lead, Pb. And that's how we do that type of question. And for one last example of alpha decay, here we have a radium 226 atom. Again, let us write out our starting species. We know that it's going to undergo alpha decay. 226 minus 4 is 222. 88 minus 2 is 86. And the element with atomic number 86 is radon. Let's move on and have a look at beta decay. Now, as a result of beta decay, the atomic number of the nucleus will increase by 1 and the mass number remains the same. So here we've got some examples. So here we have radium 228 and we've lost a beta particle, so let's see what Y equals. So this time our mass number stays the same, 228 and 0 over here, so we just have 228. 88, remember this is a minus 1, so you change the side, you change the sign, so this becomes 88 plus 1 to give us a new atomic number of 89, and if you look that up in your data booklet you will find that it is actinium. And writing our nuclear equation for beta decay of different species, here we have tritium. Again, I always write my emitting particle first because it just helps keep the numbers straight in my head. Here we have 3, 0, 3. We've got 1 over here. Remember, you change the side, you add it. So 1 plus 1 is 2. and that must be a helium atom. And for our last one here, we have strontium-90, losing a beta particle to form yttrium-90. Now, sometimes when we write decay equations, we encounter protons and neutrons. So protons can be written as, and our neutrons can be written as. And make sure that when you're writing these, you're using the lowercase letters for the symbols. Now, here are some examples of equations where you have to use protons and neutrons. So in our first one, we can see here that we have nitrogen 14 and helium 4, and after our decay has occurred, we have oxygen 17. So again, it's a maths counting exercise. 14 plus 4 gives us 18. We only have 17 here, so we must have a 1 at the top over here. 7 plus 2 is 9, and again we've got 8 over here, so we must have another 1. So this means that this is going to be a proton. And if we do the same thing here, on this side we have 4 plus 3 is 7 for a mass number, and we only have 6 over here, so it's going to be a 1 at the top. And if we look at atomic numbers, we have a total combination of 3 here and 3 over here, so that's 0. So this must be our neutron. And if we just apply that once more, we will see that we have 10, 11 over here and only 4. So this is going to be 7. 5 for a combination of atomic numbers over on the left hand side, and 2 on the right hand side, so this must be 3. And we know that the element with atomic number 3 is lithium.